So I'm going to be really careful to construct the graphs correctly and make sure that you are taking good notes on how this is done, because it's going to be important to be able to solve these problems. So the first one's going to be about graphing something called linear inequalities, which means that if you're going to graph a linear inequality, you're going to have to be able to graph a linear equation. And the reason we're going to study these is because there's a lot of realistic problems that involve linear inequalities. For example, a factory can manufacture no more than 12 items. That means it has to be equal to or less than 12 on a shift. Or a medical researcher has to be able to, or be sure they interview at least 100 patients to be sure that the new treatment for a disease is going to be better than the old treatment. So they have to have equal to or greater than 100 patients. So we're going to have to learn to associate inequality signs with words. Linear inequalities are always going to look like this kind of equation. There are linear inequalities with 3 variables, but the problem is we can't graph very well in 3 dimensions. We have to have 3-dimensional graph paper, and it's kind of hard to do that. So we use a different method for linear inequalities with 3 variables, and it's called the simplex method, and we don't usually do that in this class because it's not really required to be able to go on to calculus. Now the difference between this particular form of an equation and this equation is this is your slope-intercept form, and this is called the standard form. If you've got the standard form, you can always convert it to the slope-intercept form. But the key point here is that this sign is an inequality symbol. This means equal to or less than, which means whatever many of x plus whatever many of y added together, they can't be any more than c. They have to be equal to or less than c. Now if I replace that sign with this sign, that sign means equal to or greater than, which means c or more, whatever this number here is, or higher. If that sign points left, left means less. Lower numbers go to the left, so this is less. Notice there's no equal to. It's just less than. And in this case, this means just greater than. And what we're going to see when we're graphing is that these 2 symbols are going to be equated with an open circle in a single on a number line graph, or on a graph, a 2-dimensional graph, it's going to be a dashed line. It's not going to be a solid line. Whereas if I've got this symbol or this symbol on my graph, either one of those is going to be, if it was on a line graph, it would be a closed circle. So on my 2-dimensional graph, it's going to be a solid line. So that's the difference between the 2. These 2 both will have solid lines for the what we're going to call the boundaries. These are going to have dashed lines instead of solid ones. And the whole idea behind linear programming is to do something called optimize. Now, optimize means that you want to find the best solution that there is. And optimizing means you want to find a maximum or a minimum value of a quantity. If you're talking about profit or revenue, you probably want to find the maximum value, because that would be your optimum, or your hope would be to have the highest possible profit. But if you're talking about your cost, then you probably want to minimize your cost. So you'd be looking for the lowest possible value if you're talking about something you have to pay out. But those are both called optimization. So we're going to start out. I'm going to actually skip this part of your notes because it's just in your notes. Yes. Is it not in your notes? It should be in your chapter 3 notes. Unless I forgot to post them, which may very well have happened.
No, you posted our notes, it's just not on
Is it not on your notes?
there. No, ma'am.
I thought it was.
The notes that you would post seem to be thoroughly completion. They haven't always been the same that you've been presenting.
Okay, let me look at what your notes look like. Because these PowerPoints, I thought they matched the notes that I had up there, so. If they do not, I apologize. I would have put them in 3.1, I hope. No, you're right, it isn't in there. But don't worry so much about the definition of optimizing right now, because when we get to that, we're not going to be able to do any optimization until we get into the second and third sections. So hang on, and then I'll come back and talk about this some more. So this actually is the next thing that I showed you actually is in your notes. And that's this table. So if we were graphing these, the thing, once again, the thing I want you to remember is if I graph this, it's going to be a solid line, either that way or that way. Same thing here. This is going to be a solid line. And it's because of the equal to in there. But if I were to graph this one, it would be like this, or maybe like that, just depending on what kind of slope it had. And the same thing here, equal to, or if the equal to is there, it's solid. If there's no equals to, it's going to be a broken line. Oops. So it's always going to be dashed if it's just a greater than or a less than. And A and B can't both be 0, because that means then that you've got 0 plus 0. And unless C is 0, that's not even true. And even if C is 0, having 0 plus 0 equals 0 doesn't really give you much of a line. So let's do an example. We're going to graph the linear inequality 2x minus 3y is equal to or less than 12. And this is going to be our steps. Our first step is we're going to graph the boundary line. So I'm going to kind of slide it over here to the side for the moment. You're going to graph what we're going to call the boundary. And the boundary is this same inequality, except you write it as an equation.
Should be 2x minus 3y.
Yes, it should be, thank you. So 2x minus 3y equals 12. Now, there is a way that you can check this very easily in your calculator, and I'm going to show you how to do it. But to begin with, I'm going to show you the best way to graph a line without having to use algebra to resolve it into y equals mx plus b. Okay? The first thing I'm going to do is I'm going to find the x and the y intercepts. the x-intercept is where y is equal to 0. So that means I'll have 2x minus 3 times 0 equals 12. And when I've got that, it's easy to just say, well, you know, it's just like that 3 times 0 is not even there because 3 times 0 is just 0. So that really just leaves me with 2x equals 12. And if 2x equals 12, then I know x equals 6. So that's going to give me the point 6, 0, because remember it's always x and then y. Then the second thing we're going to do is we're going to find the y-intercept, which means we're going to let x equal 0. So that means I have 2 times 0 minus 3y equals 12. And of course 2 times 0 just disappears because it becomes 0. So that means I have negative 3y equals 12. And then y equals negative 4. So that gives me the point 0, negative 4. And if I've got 2 points where the arithmetic is not hard and I'm not likely to make a mistake, then I'm pretty sure those 2 points are right and I don't need to get another point. Those 2 points should be fine. So the point 6, 0 is right there. And the point 0, negative 4 is right there. And all I need to do is get a ruler, and I do expect you to use a ruler. And I'm drawing this boundary solid because this says equals 2 or less than, so the boundary is going to be solid. And you need to get in the habit of labeling your intercepts because in your application problems, those intercepts are going to mean something. So this is the point 0, negative 4. This is the point 6, 0. And your boundary line, you always go back to this. 2x minus 3y equals 12. Yeah, it's actually the equals. It's always going to be equals. You're graphing the boundary, and the boundary is always a linear equation. Okay? Now, we've graphed the linear equation. Now we need to solve the linear inequality. Okay? Now, the way that you do this is you need to check at least 2 points. Actually, you're going to find out you can get by with checking just 1 in a lot of cases, but we're going to check 2 points. Now, I'm not going to pick the points. I want somebody to pick me a point that will lie below this line, somewhere down here. Okay, 1, 2, 3, 4, negative 2. So there's 4, negative 2. Somebody pick me a point on the other side of the line. Negative 6 and up to 8. Now, when we've chosen those 2 points, those are called test points. We chose 2 of them, and we chose 1 on either side. And what I'm going to tell you right now is that one of these will make this inequality a true statement, and the other one won't. So we're just gonna check them both. 2 times -6 minus 3 times 8, and I want to know if that's going to be equal to or less than 12. Well, 2 times -6 is -12, minus 3 times 8 is -24, and is that equal to or less than 12? Well, -24 and -12 makes -36, and that is indeed equal to or less than 12. So that point works. Okay? That one makes the inequality a true statement. This one, on the other hand, 2 times 4 minus 3 times -2, if we try to say it's equal to or less than 12, we get 8 plus 6, which is 14, and 14 is not equal to or less than 12. Okay? No means there are no solutions on this side. Because that's not true. But there are solutions on this side. This is true. So the solutions are on that side. And the way that we show that on the graph is you take a highlighter or a colored pencil, or you take your pencil and shade with it, and you shade the side of the line where your solutions are. And by shading that, you're saying every point on this side of that line is a solution to that inequality. So all of these are solutions to the inequality. And the only way to find that solution is by graphing. There is no other way. Okay? Does anybody have any questions about the method?
Those plots, did you just pick those plots randomly? Those plots?
Yes, I said for y'all to pick them because that way I didn't influence it in any way. Okay?
As long as it's not.
Yes, that's right. And there's going to be one come up where it's on the line, where a point we're going to want to use is on the line. We're going to have to say, well, we can't use that one because we're going to have a favorite point very soon.
Yes.
I already do, but you'll like my favorite point too. So you choose test points, one on each side. One works, which means you shade. The other one doesn't. So you don't shade. Okay? That's your basic steps that we're going to go through every single time. So we're going to practice and do another one. I've only got one. Sorry.
I've got one.
If you've got your student ID number or a credit card or any kind of plastic card, that works. Those work great. And these are just what I've told you. This is just a summary of what I told you before. The graph is actually 3 sections. Above the line are the values that are, in this particular one, above the line is where there are solutions. Below the line was where there are not solutions. And the points on the line are values that actually are solutions because we used a solid line. So they're actually part of the solution. The points on the line are part of the solution. the values to the solutions of the inequality are the shaded area, and the values that are not solutions are the unshaded area. And then the values on the boundary line are solutions if the line is solid, but they're not solutions if the line is dashed. And that's why you make it dashed, to show that that's where the line would be, but it's not really there. This is just a kind of like a placeholder to say this is where it would be. So I've got a bunch of these printed out that we do not need. Now, alternatively, you can check your graph on the calculator, and I am going to show you how to do that. You check your graph on the calculator. Only I have kind of a lazy way of doing this. I don't like having to solve equations for y, because I might mess up. So this is, I know 2 steps I can do that I'm pretty sure I won't mess up. So what I'm going to do is, when I go to y1, and if I'm trying to draw the graph of 2x minus 3y equals 12, I know I've got to do 2 things. The first thing I've got to do is I've got to move the 2x over to the other side. And that means I'm going to need to subtract it. And then the other thing I'm going to need to do is I'm going to need to get rid of that -3. So I'm going to divide both sides by -3. And the way that I'm showing that I'm dividing everything by -3 is just put parentheses around the 12 minus 2x. So when I graph this, I'm going to get the right graph. And this says press zoom 6. The reason that you press zoom 6 is zoom 6 always takes you to a graph grid that looks like this. It always graphs on that window. And if you notice, then my graph grid looks pretty much on my calculator like what my graph did that I drew by hand. So this is the graph by hand, but that's the graph on the calculator. Now you can get the calculator to shade it. I will tell you that up front. There is a way to have the calculator show you where to shade it. But you have to know where it gets shaded before you can tell the calculator to do it. So I don't think it's particularly helpful to have the calculator shade it for you when you've got to figure it out for yourself how to do it anyway. Because the calculator doesn't automatically tell you that. So the only thing you really want to use your calculator for here is you want to use it just to check and make sure your graph's right. And the other thing you can use it for too is you can use it to find your x and y intercepts. If you ever need to and you've already drawn the graph, you just go to second, trace, and value will tell you, if you let x equal 0, it'll tell you where your y-intercept is. And on that same menu, second, trace, if you go down to 0 and you move just a little bit to the left of the x-intercept and press enter, and then move just a little bit to the right of the x-intercept, be sure you cross the axis, and press enter. As long as those 2 little triangles point towards each other, then it's trapped the x-intercept between them, and you can hit enter one more time and it'll tell you what the x-intercept is. And that's useful to know later to find x and y-intercepts of all kinds of different graphs. So that's the more important skill, not having it shade for you. So I'm going to skip over some of these others. I probably could have got by without printing about 2/3 of these. But Now my granddaughter will have lots of coloring paper. And we're on to example 2. So for example 2, we're going to graph the linear inequality, and notice this time it says x minus 4y is greater than. So that means when we draw this line, we're going to make a dashed line. So again, our first step is to find the x and y intercepts, so we can graph the boundary. And the boundary is x minus 4y equals 4, because it's a line. So if x equals 0, then minus 4y is equal to 4. And that means y is equal to -1. And that's going to give us the point 0, -1. And then if I let y be 0, then that means x minus 4y is minus 0 equals 4. And that gives me the point 4, 0. So now that I have those 2 points, I can go ahead and draw the line. 0, -1. 4, 0. And then you get your straight edge, your credit card, whatever you've got. And you draw a broken line. Of course, you label your x and y intercepts. And you put your equation somewhere near the line. And now we need to test the point to decide which side that we want to shade on. Now you can actually pick any point you want on this side and on this side. But there is one point that's really, really, really my favorite point. Wonder what that point might be.
0,
0,
0.
0, that's my favorite point. The origin is always my first choice. Because if I'm going to choose my test point, I like small numbers, and I like 0, 0 the best because 0, 0 makes things disappear. When you multiply by 0, they just go and they're gone. So I go back to the original inequality, and I plug in 0, 0. And 0 minus 4 times 0 is 0, but 0 is not greater than 4. That's not true. So that means don't shade where 0, 0 is. And since my line's only got 2 sides, this side and this side, and I'm not supposed to shade up here, that tells me I shade on the other side. So I shade down here. That means any point that I pick on that side solves the inequality. For example, if I want to check it out and make sure that I'm right, here's the 0.2, -4. So x is 2 minus 4 times -4. And I'm going to find out that is greater than 4 because -4 multiplied by 4 is 16 and minus -16 is plus 16. And 2 plus 16 is 18, and 18 is definitely more than 4. And I could pick any other point down here in this yellow area that I wanted to, and it would be true. So is this making sense to everybody? Okay. So let me see how far I have to go to find the next example. Here's my caution. If the point lies on the boundary line, you can't use it. Okay? Can't use that one. So if 0, 0 had been on my line, can't use that one. And just as a point of information, this link should be in your notes. Is it? That link actually is in My Math Lab. If you go into My Math Lab and go to Tools for Success, it takes you to the graphing calculator tutorial, and the graphing calculator tutorial, let me show you where it is because this will be useful to you. Everybody's going to dinner on the West Coast. If you go to, let's see, where is it? Tools for Success. Now you're on the sidebar. And the graphing calculator tutorial is right there. It's almost right across from Tools for Success. If you'll click that tutorial and then click the link on the page that it pops up for you, and it pops it up on a new page, which is good because then you can pull it up whenever you need it and then go back to working in Pearson if you need to. You can go to the basics for graphing, and it'll show you all kinds of information that'll help you with finding things, like what I showed you about finding the 0 or the x-intercept. It tells you how to right there. And the good thing is it walks you through what you're going to do. So if I want to find the x-intercepts, it says press your second and your trace button. Choose the second thing, which is your 0. And since I want to find this one, I'm to the left of it right now, so I'm just going to press enter. Then I'm going to keep pressing my right arrow until I move above it and press enter. And then press enter a third time. Oops. Oh, it wants me to get close to it. And it finds your x-intercept. And if you want to find the other one, you do the same thing. Except what you want to do this time is you got to get over closer to the other one, because it finds the one it's closest to. So I'm to the left of it now. And I move my cursor until I'm to the right of it. And press enter and it goes right to it. So that's how the tutorial works. It's really very handy and very useful to you. So just be aware that that's there. So I've given you the steps here, but we've gone through them twice now, so I think you might do was better with more practice. But now what we're gonna do is we're gonna graph a linear system of linear inequalities, which means we have two inequalities. And we're gonna have to do two steps. The first step is gonna be to take the first equation, which I'm gonna choose this one, and I need to graph y equals negative 3x plus 12. And since I've already got it in that format, the easiest way to actually graph that is to, if I could find 12 on here, I could use the slope-intercept method. This tells me that the point 0, 12 is on here. But when I look at the graph they've given me, I don't see where 12 is, it's way up here. So I could still do the method I wanted to do before. I can still say, let x be 0, let y be 0, and find both intercepts, or I can go to where 12 is, because I can see this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's 0, 12. And then the question is, okay, where do I get my next point? Well, this is the slope. So the slope tells you to go down 3 and right 1, because negative 3 is the same as negative 3 over 1. So you go from 12 down 1, 2, 3, and right 1. And there's another point. And then down 1, 2, 3, and right 1. And down 1, 2, 3, and right 1. And 1, 2, 3, and right 1. And then we actually happily landed on our x-intercept for 0. So then you grab your ruler and you draw your line. Should my line be dashed or solid?
Dash.
Should be dashed because it has less than. And so that I know which one it is, I'm going to write the equation of the line on here. But now I need to know which side to shade. And since 0, 0 is my favorite point, then I'll plug 0, 0 into the original inequality. I'm not sure where that came from on mine. I hope it's not in your notes. I just realized there was an extra y in there. Okay, good. Just printed out on mine for some reason. So then if I plug in 0, is 0 less than negative 3 times 0 plus 12? Well, negative 3 times 0 is 0, and 0 plus 12 is 12. Is 0 less than 12? Yes. So we shade. So now I'm ready to move to my other line. Yes.
How did you get the negative 3 over 1?
Get the what?
The negative 3 over 1.
That's from the number in front of the x, that's your slope. And you make it negative 3 over 1 because you can put anything over 1 to make it into a fraction.
So you don't have to find the x-intercept for y.
Yeah, you could just use your slope. You can start from your y-intercept and use your slope to find some more points. If I tell you to find the y-intercept, then you can always either plug in y equals 0 into the equation and find it that way, or you can use your calculator and find it. Okay, now I need to graph x is less than 2y. Now there's several different ways I can do that one too. But the bad news is I can't do it by finding x and y intercepts. Because if I let x be 0, that means y's got to be 0. And if I let y be 0, x has got to be 0. So I'm kind of in a quandary on that one. So to get my boundary, x equals 2y. What I'm going to do is I'm going to actually solve this one for y by dividing both sides by 2. And that gives me y is equal to actually 1/2 x, because that's 1x over 2, and I'll just pull my 1/2 out front. So if x is equal to 2y, then y is equal to 1/2 times x. And since it's 1/2 times x, I know that y equals 1/2 times x plus, I can add a 0 for my y-intercept because I'm not adding anything to the equation. 0 doesn't change anything. So that means my y-intercept is 0, 0. Which tells me I'm not going to get to use this test point this time. And it also tells me that I can go up 1 and right 2. Because my slope is 1/2. So from there I'll go up 1 and right 2, and up 1 and right 2, and up 1 and right 2, and up 1 and right 2. And I've got more than enough points now to know where I need to draw my line. And again, my line needs to be dashed because it's less than. It's the line x equals 2y. And you can verify that because, for example, this point is 2, 1. 2 is equal to 2 times 1. So you know that you've got the right points. Now, I can't test 0, 0. I'm going to have to find something else to test. Anybody have a particular point you like? -4, 2? Okay, we'll check that one. So if we go back to our inequality, -4, 2, what we're saying is -4 less than 2 times 2? And 2 times 2, of course, is +4. And -4 is less than +4. So that means we need to shade that direction. But then the question that we have is, where is the solution to the system? Because we have 2 inequalities here. Where are there points that work in both? It would be right here. Because all of the blue area works in the top equation. All of the orange area works in the bottom equation, so where it's blue and orange is the solution. So this is the solutions to the system. And they're in this area here. Place where it's double shaded. Now, you can tell real quickly that if you were to have more than two equations, this is going to get really muddy and really hard to read really fast. So when we do the next one, I'm going to show you a way that you can do this without having double shading. So does anybody have any questions on this one? Everybody got all your details ironed out? Okay, let me look for my next one. Now, before I go too much further, I need to give you another vocabulary word here too. This area where the solutions are, that's called the feasible region. So my feasible region is here. It's that part. And the reason it's called the feasible region is because that's where solutions are that are feasible for both sets of inequalities. So the region that's the overlapping parts is called the feasible region. And for our next example, this one tells us graph the feasible region for this system. So the first thing we would do is we would need to graph that equation, not the inequality, but the equation is the boundary value. And I thought I had a piece of graph paper, but apparently I do not. So let's see what I can do here. If you have some, I would, yeah, it would be quicker. Way to print it out. Thank you. So let me show you from scratch how to do this one, and then you won't have to do the double shading here. So I'm going to just copy these onto this. We have y is equal to or less than negative 2x plus 8y. And then our other equation for inequality is negative 2 is less than x is less than or equal to, and that y is not supposed to be there on either one of these. I have no clue why my printer printed those off. That should be just 1. So let's look at how we would go about graphing these. First we need an x and a y axis, so I'm going to draw those. This is 1, 2, 3, 4, 5, just so I have some reference marks. 1, 2, 3, 4, 5, that would be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll make it easier to plot our points. So then the first thing I'm going to do is I'm going to graph the boundary of y equals negative 2x plus 8. So I know that the y-intercept is going to be 0, 8. So 6, 7, 8. And from there, I'm going to go down 2 and write 1. And then down 2 and write 1. And down 2 and write 1. And down 2 and write 1. And just happen to have found my x-intercept, which is 4, 0. So we're going to draw the line, and this is going to be a solid line. Because it says equals 2. So everything on that line is actually a solution to that inequality. Now, in order to decide which way I'm going to shade, I'm still going to test my old buddy 0, 0. So if I take 0 for y and 0 for x, then I have 0 is equal to or less than negative 2 times 0 is 0 plus 8 is 8. 0 is less than 8, and that's true. So that means when I get ready to shade, I'm going to want to shade that direction. And notice I didn't actually shade, I just drew some little arrows saying I'm going to shade on that side. Okay? Then I'm going to go about trying to figure out how to graph the rest of this, because the rest of this is a little complicated. When you see what's called a compound inequality, because that's what that's called, is a compound inequality, there's only one variable there, that's x. What kind of line does an x equals graph look like? Is it back and forth or up and down? It's up and down, because it has x values. X never changes. No matter what y says, x never changes, so that means it's going to go up and down. The first thing you're going to have to look at is, where is x as far as these two numbers? What's the word that it is? It's in between those two numbers, okay? It's between those two numbers. So I need an x equals line at negative 2. And I need an x equals line at 1. The one at negative 2 needs to be a dash line. The one at 1 needs to be a solid line, because there's an equals there. So I'll go over here and I find the point, x equals 1. And I draw a straight up and down vertical line at x equals 1. Has a y-intercept of 1, 0. Then I go find where x is equal to negative 2, and I'll draw a straight up and down vertical line through negative 2, 0. Only this time I use my broken line. Now, where does this say the x values I want are? They're in between those two. Or if you tested 0, 0, is 0 between negative 2 and 1? Yeah. So that means my test point worked. That means that I'm going to shade in between these two lines. But because I'm shading below the green line, my shading isn't going to go all the way. My shading is going to go between them. continue on down there, but it's gonna stop inside that green line because I'm shading below that green line. So that's my feasible region. That yellow region is my feasible region for that set of inequalities. So you see how making the arrows helps you shade properly without having so much colored on your graph? And we are going to have systems where we may have 3 or 4 or 5 equations that we have to shade one way or the other. So it's better just to point an arrow which direction you're going to go until you figure out at the end what your feasible region is, and then shade only your feasible region. So we've graphed that feasible region and we've determined that it looks like this. Okay? Questions so far? Okay, let's see. Here we're going to graph the feasible region for the system 2x minus 5y is equal to or less than 10, x plus 2y is equal to or less than 8, and then x is equal to or greater than 0 and y is equal to or greater than 0. Now there's actually a really easy way to get around 2 of these restrictions. What does that tell you about the values of x that we're looking at? They're all going to be positive. And this tells you that the y values that we're going to be looking at are all going to be positive. So which quadrant has positive x and positive y? Quadrant 1. So the best way to draw this graph, and this time I'm going to wing it and not use graph paper. Is to stick to the first quadrant. So we've already taken care of both that and that. We don't even need to draw the other quadrants. They're not included in our solution. Now looking at x plus 2y is equal to or less than 8. If x is 0, y is going to be 8 divided by 2 is 4. If y is 0, x is going to be 8. So I've got my 2 points. And this is why the x and y intercepts are so important, because it lets you draw these on here and not have to worry about finding tough points or hard points. So I am gonna try to keep it to scale though. So I've got my ruler here, and I've got to go 0 or 8 0. So here's 1, 2, 3, 4, 5, 6, 7, 8. So here's 8 0. And then up the y-axis, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 0, 4. My line would be solid. If I test 0, 0, that means 0 plus 0 is 0. Is 0 equal to or less than 8? Yes. So I'm going to shade that side of the line. And that's the name of my line. How did I get the 8, 0? If I let y be 0, then 2y disappears.
That's,
Yeah, but still, if I say x plus, yeah, it's 0, it doesn't matter. Okay? So then I'm going to do the same thing with 2x minus 5y is equal to 10. If I let x be 0, then negative 5y is equal to 10. That means y is equal to negative 2. And if I let y be 0, then 2x equals 10, and x is equal to 5. So I need to plot the 2 points. Well, see, I can't really plot negative 2, 0. It's not on my graph. I can kind of see where it is, but it's not going to be part of my solution. So here's negative 1, negative 2 is right at the bottom of that black. So I can still figure out where it is. And then 5, 0, 1, 2, 3, 4, 5. So I'll still connect up those 2 points. And again, I'm going to use a solid line because it says equals to. The part I'm most interested in is this part here, because this part down here is not really helping me much. So again, I'm going to test 0, 0. Is 2 times 0 is 0, minus 5 times 0 is 0. Is that equal to or less than 10? Yes. So that means on the red line, I'm going to be shading that direction. I'm going to be shading above the line, not below it. So if I shade above the line, then the part that's my feasible region, staying inside the first quadrant, is this part right here. So that's my feasible region. And there's actually a name for this kind of region because there's 2 different kinds of feasible regions. This one is called a bounded feasible region. Because it has boundaries on all 4 sides. Okay? It's actually closed in. So we're going to do an example now of one that's unbounded. So this is the one that we just found. And actually I can go back because I can show you some of the other examples. This feasible region is unbounded. The reason it's unbounded, it's bounded here, here, and here, but it's not bounded down here. It continues onward. It's not closed off. It doesn't end. And this first example that we did, this is also an unbounded feasible region, because even though it's got a boundary here and here, it continues on into in that direction. It keeps going on forever, so it doesn't close off. It's not an enclosed area. Bounded means it's actually enclosed. got one more example. And then I think after this, I think we've got an application. Yeah, we've got an application. We're finished with this section, so we'll take a break. So we're going to graph this system. We've got three inequalities. One of them is the easiest one to get, is going to be the y is equal to or less than 1. We know that y equals 1 is the horizontal line. So we may as well just go ahead and put that on there. And since it says equal to or less than 1, well, certainly 0 is less than 1. So that means we're only interested in the part of the graph that's below that line. So then our next piece would be x plus 3y is equal to or greater than 6. So if I let x be 0, and I cover up x and I have 3y equals 6, which means y would be 2. And then if I let y be 0, if I cover up y, then I have x equals 6. So my points are 0, 2, and 6, 0. Draw your line. And it would be filled in because it's equal to or less than. It's going to be a solid line. And 0, 0 says 0 plus 0 would be equal to or greater than 6. No, it's not. So we don't shade towards 0, 0, we shade the other direction. We'll shade above the line. So right now we're looking at a feasible region that's just right here. And then we check this one. Negative 3x plus 4y equals 12. So if we let x be 0, then that means 4y equals 12, y would be 3. And if we let y be 0, that means negative 3x equals 12, and x equals negative 4. So we have negative 4, 0. And we have 0, 3. So we draw that line. Then test 0, 0. 0 plus 0 is greater than 12. No, it's not. So we don't shade towards 0, 0. We have to shade again above that line. So this is going to be interesting. We have to be below this line So nothing up here. You have to be above this line. And we have to be above that line. So even though this solves two of them, and that solves two of them, is there anything that solves both of them? Nope. There is no feasible region. Not that solves everything. And if this resulted from a manufacturing process, you'd be sitting there saying, why am I making this stuff? Nothing works. Okay? No configuration I can come up with is going to satisfy all of these. Are called constraints. So nothing I can come up with is actually going to satisfy the limitations of my business. And sometimes there is no solution to a particular problem, and you have to actually make a change to the process. So like we saw here, there's no solution to that set of inequalities. Now, since it's 7:30 and you've been sitting for an hour and a half, I think before we actually do the manufacturing problem, I think I'm going to give you all a break. Let's take a break till about 7:45, and then we'll finish as much of this. We'll finish this section and as much of the next section as we can. Okay, so here's our application example. And I actually could skip over all the rest of the examples to some extent and just work from this one, but I'll do another different example too, to give you more than one. So the information we're given in the problem, it says that manufacturing one batch of the cake cones takes 1 hour in the mixing department and 2 hours in the baking department. So we've got, like we had in the last chapter, we've got two things going on. We're making two different items, cake cones and sugar cones. And we don't know how many to make of either one, which is why there are variable X and Y. And we've got two departments. We have a mixing department and a baking department. So for the cake cones, we need 2 hours, or 1 hour in the mixing department, which is this one, and 2 hours in the baking department, which is that 2. And then for your sugar cones, which is the Y, they take 2 hours in the mixing department and 1 hour in the baking department. And then following through with that, this is where our constraints come in. It says each department is operated at most 12 hours a day. So the number of hours in the mixing department has to be equal to or less than 12. And the number of hours in the baking department has to be equal to or less than 12. So that actually gives us in our equations, because our equations are 1x plus 2y is equal to or less than 12. There's our first inequality. This is our first constraint. That's the name of these. And then for our second one, 2x, 2 hours per cake cone, plus 1 hour per sugar cone is equal to or less than 12. So there's our second constraint. So what we want to do then, and I'll go probably a little faster through these because you should already have the graphs but they'll be up here so you'll be able to fill them in too. These don't have to be as neat. That one out of the way. So we need to graph the feasible region. So when we graph that feasible region, what we're going to do is we're going to take those constraints, the x plus 2y is equal to or less than 12, and we see there that if you let x be 0, y is going to be 6, and if you let y be 0, then x is going to be 12. So here's 12, 0. Here's 0, 6. So this is the constraint x plus 2y equals 12. And if you test 0, 0, 0 is in fact equal to or less than 12. So we'll get that out of the way. I'll put it over here. So 0 is equal to or less than 12. So that means that I'm going to shade below that line. So then moving to the other constraint, 2x plus y is equal to or less than 12. Well, if I use 0 for x, that means y is equal to 12. And if I use 0 for y, that means x is equal to 6. So that's going to be this line. And again, 0, 0, 0 is equal to or less than 12 is true on both of those. So we're going to shade towards 0, 0 on this one. So that tells us that our feasible region is a bounded feasible region. And when they ask you part C, and part C is the one that says, can you make 4 batches of cake and 6 of sugar? I'm sorry, 6 of cake and, let me go back and read my problem again. Yeah, 4 cake, 6 sugar. Then that's going to be 4 and up 6. It's going to be that point right there. Is that point in the feasible region? No. You can't make 4 batches of cake cones and 6 sugar. Won't happen. Because it exceeds your available baking time. However, you can make 3 batches of cake and 2 batches of sugar, I think it is. Because here, this is 2, 3, and up 2 would be right there. That does fall in the feasible region. So, that one is possible because it's in your feasible region. And what we're going to see in the next chapter is that we're going to have our constraints, which are those 2. This is the other 2 constraints because obviously you can't make negative cake cones, you can't make negative sugar cones, you can't unmake any of them. So your constraints give you what are called corner points. 0, 0, of course, is always going to be one of your corner points. if it's a bounded region, or it may be one of your corner points. But you also have some other corner points. You have the corner point 0, 6, and you have the corner point 6, 0. But you also have a point, and it's probably 4, 4 looking at the graph, which is one of your corner points. So it's going to be important that you be able to find the intersection point of the two lines. Now there's two ways that we're going to be able to do that. We can either graph it on the calculator and find the intersection point. You do that using that second trace menu, the calculate menu, and go down to number 5 for intersect. But we just left a chapter that told us how to solve a system of two equations using matrices. So the other method defines your corner point where they intersect, because remember these others are either the origin or x and y intercepts are your other corner points, but you need the intersection point. That's the solution to the system of equations, x plus 2y equals 12, and 2x plus y equals 12, which gives you the matrix 1, 2, 12, 2, 1, 12. And if you do the reduced row echelon form of matrix A, it will tell you what that point is. So this is where chapter 2 still comes in. And that tells you that the reduced row echelon form of matrix A is 1, 0, 0, 1, and your solution out here, 4, 4, is right there. So that tells you that this is, in fact, that other corner point. So you need to remember how to do the last chapter while we're doing this one. They're very closely tied together. So we've graphed the feasible region and then used the feasible region to determine that this is not possible, but that one is. Okay? So now we need to get a little terminology down. I've been using the right terminology as we go along, but I want to make sure that we keep up with it. Most of the models that we're going to solve are going to involve finding an optimum value. Remember I told you we were going to talk about that some more. So we're talking about finding an optimum value, which is either going to be a maximum or a minimum. It would be a maximum if you're talking about probably revenue or profit, because that's money coming in. We want the most money coming in as we can get. But it might be a minimum if we're talking about cost, because one way to maximize your profit is to try to minimize your cost as long as you don't compromise the quality of your product. So we're going to want to find optimum values of a function, and the function that we're going to be trying to find the max and the min of is going to be called the objective function. And that objective function is going to be an expression for either revenue or cost or profit, one of those three commodities. And it's going to satisfy those set of restrictions. That's your inequalities, and we call the inequalities constraints. things that are kind of boxing us in. And as long as we've only got two variables involved, then we can find the answer to the problem by graphing the constraints, finding the feasible region, and then using our corner points to see which of the corner points optimizes your objective function. So that's going to be the process we follow for this whole chapter. So here's an example, totally out of context, so we don't have to worry about understanding what the problem's asking. You know, this is just how do you solve the problem. So what we're going to do to solve this problem is, first of all, we realize that that puts us in quadrant 1. There's no point in going anywhere in quadrant 2. This is going to put us in quadrant 1. So these are going to be our two constraints. 2x plus y is equal to 4 is going to give us our first boundary. And negative x plus 2y is equal to 4 is going to give us our second boundary. They both are going to have solid lines because they're equal to or less than. And we're going to be able to test 0, 0 in both of them because 0 plus 0 is equal to or less than 4. Is true. And negative 0 plus 0 is still 0, and 0 is equal to or less than 4 is still true. So the origin is one of the corner points because it satisfied both of those. So that's the first thing we're going to know, and we're going to shade toward the origin. So that's just a quick summary of what I'm going to show you, rather than taking the time to carefully plot out the graph. So if you graph, if y is 0, x is 2, if x is 0, y is 4. Wait, I've circled the wrong one. This would be 0, 4. So if y is 0, x is 2, so that would be this one. If x is 0, y is 2. If y is 0, x is negative 4. Which is way back here, and we don't actually need to graph that. Now, one easy way to do this would be to actually graph these on your calculator. Move 2x over to that side. And do the same thing here. Only this time it'll be y equals 4 plus x, and then you need to divide that by 2. So you could graph those on your calculator if you wanted to. But since 0, 0 satisfies both of them, because we find out that we're going to shade towards 0, and we're going to shade towards 0, then we've got the feasible region. Our feasible region is bounded. Sometimes when your feasible region is unbounded, if you're looking for a maximum, you're not going to be able to find it because none of your points are going to ever maximize anything. They're all going to be at the bottom. But this feasible region is bounded, so that means we could maximize or minimize whichever one that we needed to. And the way we figure out how to do that is, first of all, we need the coordinates of point A. Because we've got this corner point, it's a y-intercept. And we've got this corner point, it's an x-intercept, but we need the coordinates of point A. In order to find the coordinates of point A, what you need to do is you need to find the reduced row echelon form. This is the quick way of 2, 1, 4, -1, 2, 4. Since I've already got that up there, I'm just going to hit second enter because I've already changed matrix A. And I see that I get decimals, so that means I know they're fractions. So I'm going to go to the fractions, and my corner point A is 4/5, 12/5. There's how you find your corner points. You use what you learned in the last chapter. Does anybody have any questions this far? Because pretty much none of this was new.
Question, how do you know which way to shape your line, up or down?
Well, remember we checked 0, 0 in both of the inequalities? So I'm going to shade from the line toward 0, 0.
That's if the statement's true, right?
If it's true.
Okay, so
If it's not true, then you shade away. Okay, and if it had not been true, then we would have shaded out this way and up that way, and our feasible region would have been up here, and it would have been unbounded. Okay? That's a good question. Okay, so we've got our graph, and I already told you what corner points are. So, let's see, did they give us an objective function? Yes, okay. So let's go back and get the objective function here. So I'm going to go back to the example 1, and it says maximize or find the maximum value of the objective function. So there's our objective function. So for the objective function, we need the corner points. So our corner points were 0, 2, 2, 0, and 4/5, 12/5. Of course, 0, 0, but if I plug 0, 0 in here, then Z is going to be 0. So that's not going to be a maximum. At least we hope not. So what you do now is you remember that this is X, this is Y. So Z in this case would be 3 times 0 plus 4 times 2, which would be 8. If X is 2 and Y is 0, then Z would be 3 times 2 plus 4 times 0, which would be 6. And then this is the tough one. Z equals 3 times 4/5 plus 4 times 12/5. And since I don't really feel like doing arithmetic in my head or on paper, I have a calculator that does arithmetic. So 3 times 4 divided by 5 plus 4 times 12 divided by 5. And let's just change it to a fraction since we've got fractions. And it comes out to be 12. So the corner point that maximizes our value of Z, our objective function, is this one. and our maximum value of z is 12. Don't always assume it's going to be the intersection of the lines. That's not true.
So it's not always.
It's always a corner point, but it's not always the intersection corner point. It is entirely possible, if you do this problem, where did I put my graph? Ah, there it is. It is entirely possible that when you're maximizing something, that this won't be the one that maximizes things. It is possible. Not necessarily every time, but it is possible that that might be the maximum, or that might be the maximum. It just didn't happen to be this time. Now, if you're looking for a maximum, I hope it's obvious that that's never going to be a maximum. Okay? And if it's a minimum, it doesn't do you any good. So let's do one that's not completely stripped of all meaning. Let's do an application problem. Well, no, let's go ahead and do this one since we got it, just for the practice. We've got enough time. So this is our objective function, just so you get used to the language. These are our constraints. And this is telling you, once again, don't bother graphing anywhere except in quadrant 1. And that's going to be true for just about any application problem you're ever going to do. So what we need here, we would find the x-intercepts and the y-intercepts of both of these boundary regions. And then we would also find out where they cross. So before I ever go to the graph, I'm going to go ahead and find their intersection. 1, 2, 10, 3, 1, 10. And I'm going to do the reduced row echelon form of that. Okay, so that looks right. And it says the solution, or the intersection point, is going to be 2, 4. So that's going to be my intersection point. That's going to be one of the corner points. I already know that up front. Now without graphing, I don't know what the others are. So I need to go to a graph. And we're just going to do a sketch of one here. So limiting it to quadrant 1. I know that x plus 2y is equal to or greater than 10. That means that x plus 2y equals 10 as a boundary. If x is 0, y is 5. If y is 0, x is 10. So I'm just going to sketch the graph. And 0 plus 0 is 0. Is 0 equal to or greater than 10? No. So I'm not going to shade towards 0. I'm going to shade up. So then I move on to the next constraint. 3x plus y is equal to or greater than 10. If x is 0, y is 10. let's see, that's 5, 6, 7, 8, 9, 10. And if y is 0, x is about 3 1/3, 10/3. So about right there. And again, 0 is equal to or greater than 10 is not true. So I'm going that direction. I've already found this point using my matrix solution. So this is the point 2, 4. And I know I'm shading out this direction. So my other two corner points are 10, 0. This point right here. And 0, 10. For that point right there. So what I want to do with that is I want to go get my objective function. And notice here I want to minimize it, not maximize it. I want to find the smallest value possible. And it's going to be either that point, or that point. So for 2, 4, z is equal to 2 times 2 plus 4 times 2, which is 4 plus 8, which is 12. For the point 10, 0, z is equal to 2 times 10 plus 4 times 0, which is 20. And then for 0, 10,
You've got the first equation, you've got 2 times 2 plus 4 times 2, it should be
4 times 4. Thank you, thank you. So that would be 16 plus 4 is 20. So far I've got two 20s, which means that I get the same thing here as I do here. But then same thing here as here. Those two are equal. But then if I take z is equal to 2 times 0 plus 4 times 10, z is equal to 40, so that's worse. So that means I can minimize it here or here and have the same thing. So it is possible to have two minimum values, but it's because they're identical. Okay? So you can minimize your objective function with 2, 4 or with 10, 0, but not with this one because it's too big. We're trying to find the smallest. You look doubtful. Okay, we're not always trying to, suppose this was a cost function. Would you want your cost to be the most it could be or the least it could be? Okay, well that would happen if I either made 2 batches of A and 4 batches of B, or I could also minimize my cost if I made 10 batches of A and didn't make any of B. And that might not be feasible in the application I'm doing, so I might have to do that one, but I would be at the same cost either way. I will still minimize my cost function. Does that make a little bit more sense?
She's got to plug all in the same equation to see.
Yeah, you're plugging all of them into your objective function. Your objective function is always called z. And you have to look and see, do you want to minimize it or do you want to maximize it?
How do you know which point to use?
You always use your corner points. Your corner points are going to be where there's a corner of the feasible region. So here's your feasible region. So that's why this is 1, and this is 1. Because it makes sharp corners there. Okay? Okay. And this just says that your maximum or minimum is always going to be at a corner point. I left out all the part about proving that because that's more trouble than it's worth. You don't care about proving it, you just want to know it works. So this is the summary. Is this on your notes? This is the summary of everything that we do to solve these problems. Okay. Well, I will actually post this slide then in your section 3.2 so that you can actually put this down so you can follow these steps. Okay, rather than do another max and min problem, I'm going to skip over example 3 and go to an application because it helps to do an application. So we're going to go on into the next section.
Can I ask a quick question? I'm sorry.
Sure.
So whenever you're trying to figure out which way to shade, you do like 0, 0 as your checkpoint. Do you plug in the X and the Y as 0, or do you just do the?
You plug in both X and Y as 0 because 0, 0 says X is 0 and Y is 0.
Okay, so if I were to use like 2, 4, I would plug in 2 different.
Yes.
Okay.
Yeah, you can use other points, but 0, 0, unless it's on the line, 0, 0 is always an easy one to use.
Okay, so does it have to be above or below the line? Or does it matter? Just,
It has to not be on the line. It could be either above or below.
okay.
And then you shade in toward the one that works. Okay? All right. We'll talk about canoe rentals here for a minute. Mr. Potato's gonna open a new business called River Explorers, and he rents canoes and kayaks to people to travel 10 miles down the Clarion River in the Cook Forest State Park. Now, we really don't care how far they travel, okay? We're not interested right now in that. We do know, and we are interested in, that he has $45,000 to purchase boats. We also know that canoes cost $600 each. And kayaks cost $750 each. And we know that he has a dock that'll hold up to 65 boats. So right away, I think you can see that the variables here are how many canoes should he buy and how many kayaks should he buy. Okay? Well, he's constrained by the fact that he has $45,000. So for every canoe he buys, it costs him $600. And for every kayak he buys, it costs him $750. So when he adds all that money up, he can't go over $45,000. He also knows that he only has space for 65 boats. So when he adds the canoes to the kayaks, he can't go over 65 of them. These are his constraints. He's constrained by money and he's constrained by space. Two things he has to stay within. Then we go on and keep reading, and it says he can rent his canoes for $25 a day. That'll be $25 times X. And he can rent kayaks for $30 a day. So 30 times Y. And if he adds the total amount of money that he makes for canoes and kayaks, that's called his revenue. Or actually, I can't say it's revenue for X, it's the revenue for XY, whatever those two numbers are. So this is his revenue equation. What do you suppose he wants to do with his revenue equation? He wants to maximize his revenue. He wants to make the most money he can. Okay? So this is gonna be what we look at graphing. This is what we're gonna actually plug numbers into at the end. This is our Z function. And you can call it Z equals if you want to, or you can recognize it as revenue. But he wants to maximize his objective function. So what we're gonna do to solve the problem, in the first place, it's gonna be kinda hard for me to think about graphing x plus y is equal to 65 on the same set of axes as this. But I can use something I learned about matrices to come up with an equivalent equation that'll have the same solutions. So what we're gonna do next is a little algebra trick. You don't always have to do it, but sometimes it helps when you're talking about money. So what we're gonna do, since this is our system, but those are awfully big numbers, we can actually divide everything here by 150, because 150 divides into all of those. And as long as you divide everything by the same number, you keep the same solutions to the equation. That's what we learned in chapter 2. So by dividing all of those by 150, we come up with easier things to graph. So 150 into 60 gives us 4x, 150 into 750 gives us 5y, and 150 into 45,000 gives us 300. And I think I can probably get those on the same set of axes. It might work out a little bit easier. And then there's the additional constraints that you can't have negative kayaks or canoes. The least you can have of either one's going to be 0. So that's going to put us in the first quadrant. So from this equation, here's what we know. We know that if x is 0, y is going to be 65. And we know if y is 0, that x is going to be 65. So that's going to give us 2 points for that graph. And then if we look at this one, if we let x be 0, then 5y is equal to 300 and y is equal to 60. And if we let y be 0, then 4x is equal to 300, and 4 goes into 375 times. So there's our x and y intercepts. Some of those are going to be corner points. And while I'm still looking at this, I also need to find where these are going to intersect, because that's also almost without a doubt going to be a corner point. So what I want to do is go ahead and do RREF of the matrix 1, 1, 65, 4, 5, 300 to find where those two intersect. So 1, 1, 65, 4, 5, 300. And the point 2540 is going to be where they intersect. So there's all the information I've gathered before I start. Okay? So now that I've got that information, so we can kind of look at this all at one time. Here's the graph that we come up with. The 65.0 and the 0.65 tells us that this is one of the corner points. And then 0.60 is one of the corner points. And we know that this is, we were pretty sure all before we ever started that was going to be a corner point. So that's our intersection point, 2540. So here's our three corner points. We know, going back to the inequalities, that if I let the point 0, 0 be tested, 0 plus 0 is 0, and 0 is equal to or less than 65. So that tells me that for that first line, which would be this one, I'm shading towards 0, 0. And 4 times 0 plus 5 times 0 is 0, which is definitely less than 300. So I'm also shading below this line. So that tells me that this is the feasible region. And since I'm talking about revenue, it doesn't make any sense to minimize your revenue. You want to make lots of money. So your revenue equation from down here is $25 a day for rent on canoes and $30 a day for rent on kayaks. And we're going to plug in our corner points, 0, 60, 65, 0, 25, 40. So Z is going to be 25 times 0 plus 30 times 60, which is going to be, that's 0, but this is going to be 1,800. Whereas if we have 65 canoes and no kayaks, so 25 times 65 is going to be 1,625, so we won't make as much money. So then we only have one more. 25 times 25 plus 30 times 40 is 1,825. So there's the answer to our question. The maximum revenue will be $1,825 per day with 25 canoes and 40 kayaks. So this is why you need to learn how to do this. If you're starting a business, you want to be sure you make the most money you can. Okay? Now, given that you haven't forgotten any of chapter 2, I'm crossing my fingers here. If you haven't forgotten chapter 2, this new chapter shouldn't be too hard. It should just build on what you already had. But if you had trouble with chapter 2, please let me know. Come let me help you. Either that or go see Mrs. Perry in the Learning Center. The bad news about Mrs. Perry in the Learning Center, though, is I don't think they have any evening hours. I think it's mostly daytime hours. But I would still check and see. Okay? Questions? Okay, we probably have time for another one. Just to be sure you do have it. Let me pull this one on down here. Even if all we do is set it up, I think it'll help you to have it set up, then you can check your answer once you know how to set it up. So, okay, we've got a 4-H member that wants to raise only goats and pigs. She doesn't want to have more than 16 animals. Now, without going any further than that, we're going to stop right there. What do you think your variables are going to be? And why pigs? Okay. X equals goats. Y equals pigs. Okay. What does she wants to raise no more than 16 animals tell you? Okay. So X plus Y is going to be equal to or less than 16. And of those 16, she doesn't want any more than 10 goats. What does that tell you about X? Okay. So we took care of that. We took care of that. So now we can keep reading. We'll go to the second sentence. She spends $25 to raise a goat. And she spends $75 to raise a pig. And she has $900 that she can spend on her project. What does that tell you? Okay, she has to spend less than equal to or less than $900. So it costs her $25 per goat, 25x, plus 75y, because it costs 75 to raise pigs. We go to the next sentence. Each goat produces a profit of $12. That's 12x. And each pig produces $40. Because everybody likes bacon better than goat, I guess. So how many pigs and how many goats should she raise to maximize profit? Okay? She wants to maximize her profit. So we're going to use these three to graph. And then we're going to get corner points. And then we're going to plug the corner points into the profit equation. Now, in the table, we could have set that up as a table. But as you saw, we didn't actually have to. As we read the problem, we can actually come up with the table as we go along. But we came up with the same table that they did. So here's her setup. This is her profit equation. And she wants to maximize that profit. So we're going to maximize this. So there's your objective function. And here's your constraints. And of course we can have negative pigs and negative goats. So once again, that just tells us we're going to have to stay in quadrant 1. So just for the things that I know from looking at this, the x and y intercepts here would be 0, 16, and 16, 0. If x is 0, y is 12 for this one. And if y is 0, x is 36. And I know that that is going to be a vertical line through the point x equals 10. And then I'm going to graph to the left of that line because I've got to go less than. Because that's x is equal to or less than 10. So here's what our graph is going to look like with those constraints. Let's see if I can back this out where we can see both of them. So here's the equation that tells us how many animals we've got. Here's the equation that tells us how much they cost. So there's the cost equation. Here's the equation that tells us her personal preference not to have too many goats. Maybe she doesn't have space for more than 10 goats. And if you look back at these equations, 0 is equal to or less than 16, 0 is equal to or less than 36, 0 is equal to or less than 10. So we're shading every time towards 0, 0. So this is our feasible region. So one of our corner points, you can see here, one of the corner points is 0, 12. This corner point is going to be 10, 0. You could solve this one by doing a matrix, but you don't need to because you know that x is 10, so all you really need to do is plug in 10 into this. And you know that y is equal to 6. So you didn't need a matrix for that one. So that's got this corner point, this corner point, this corner point. Now we need to find this one, which means we need to solve the system of equations for these two. So we've got x plus 3y equals 36. x plus y equals 16. And we'll do the RREF for that. And that gives us that corner point is 610. So now that we've got all of our corner points, and since it's getting a little bit late and my brains might be getting tired, what I'm going to do is I'm going to go to the y equals menu, and I'm going to plug in the objective function. Remember, her objective function is about profit. Well, I really can't. Doggone it. Looks like I might have to do it the hard way. Because I've got X and Y. So we're going to have to do this one by hand. So using our corner points, 12 times 0 plus 40 times 12 for the first point is 480. Ten 0 is only going to be 120. So it's not going to be that one. We already know that. 10 6 is going to be 120 plus 240 is 360. So this one's still good so far. So the last one is 610. So this is 72, and that's 400. That would be 472. So actually our maximum profit comes from what? Goats, or I'm sorry, no goats, and 12 pigs. People really do like bacon better. Okay? So remember what I told you about, that it wasn't always going to be one of the intersection points? Sometimes it's going to be one of your, this time it actually is an intersection point, but it isn't the one that looks like it ought to produce the most. Because this point, if you think about it, looking at that graph, is higher than the other one. But because of the ratio of profit for the pigs and the goats, this actually produces more money. I'm sorry, not that one. 0, 12. This one actually produced the most profit. Okay? So do you think you can handle those? I will post a practice test for you. It will be up probably within the next day or two. And then you'll have through Sunday night to get it done. I'll post the answers to it. If somebody wants them earlier than Sunday, then I'll post them if they ask me. But I will not post them until probably Saturday or Sunday to give you time to actually do your practice test. Okay? Because I know most of you can't do a lot of work until the weekend. So you might have any questions or any comments? Have a safe trip home, and hopefully a dry one. Although I think it probably is still raining. Well, we really can't fuss too much because we need the rain. That we do.